Last episode we built a mesh and named its edges moving wall, fixed walls. But naming an edge doesn't tell the fluid what to do there. Today we fix that. Boundary conditions intimidate people because they look like a long list of magic keywords. They're not. By the end of this, you'll see every one of them is a variation on just two ideas. Start with why. Our simulation only covers a finite region, the domain has edges. But the fluid inside doesn't know what's beyond those edges unless we tell it. Inside, the equations march forward. But at every edge, the solver hits a question: what's the velocity here? What's the pressure? Without an answer, the maths has no unique solution. A boundary condition is simply the answer we supply at each edge. It closes the problem, turns infinitely many possible flows into the one we actually want. Here's the secret that demystifies the whole list. At heart, there are only two kinds of boundary condition. The first is Dirichlet, you fix the value itself. Fixed value. You're saying, the velocity right here is exactly 1 meter per second, full stop. The second is Neumann, you fix the gradient, the rate of change. ZeroGradient is the common one, whatever the value is just inside, it leaves the boundary unchanged. Nothing is imposed, the flow just continues out. Fix the value, or fix the change. Almost every boundary condition in OpenFOAM is one of these two wearing a costume. So let's meet the common named conditions, each one a physical situation, not just a keyword. NoSlip, the everyday wall. Real fluid sticks to solid surfaces, so velocity is zero there. It's just a fixed value of 0, named for clarity. Fixed value, any imposed number, the speed at an inlet, or the moving lid in our cavity. ZeroGradient, the natural outlet. Let the flow leave without forcing a value on it. Symmetry, if your geometry mirrors simulate only half. It halves your cell count for free. Empty, the two-dimensional switch. It tells OpenFOAM not to solve in that direction at all, that's how we do 2D. Now the part that trips everyone up: how do velocity and pressure work together at an inlet and an outlet? There's a simple rule. Picture flow through a pipe. Flow enters the left, leaves the right. The rule: at the inlet you fix velocity and let pressure float. At the outlet you do the opposite, fix pressure, let velocity float. It's a seesaw. Wherever you pin the velocity, you must let pressure be free, and vice versa. Fix one, free the other. Which brings us to the mistake every beginner makes exactly once. Watch. You fix both velocity and pressure at the same boundary. It feels like you're being precise. You're actually breaking it. Pressure and velocity are linked by the equations themselves. Pin both, and you've told the fluid two things that can't both be true. The problem is over-specified, and the solver either diverges or gives nonsense. So the golden rule: at any boundary, for this pairing, fix one and free the other. Never both. Let's read our cavity's velocity file with new eyes. Every line should now make sense. The moving lid, fixed value, 1 meter per second, a Dirichlet condition. The other walls, noSlip, the fluid clings to them. And front and back, empty, because this is a two-dimensional problem. No magic. Just the two ideas: fix the value, or fix the change, apply to each edge of the box. That's boundary conditions. Two core ideas, a handful of named conditions that are physical pictures, the inlet-outlet seesaw, and the one rule that keeps your solver stable: never fix both. We've got a mesh and we've set the physics at its edges. Next episode we open the two files that decide how the equations are actually turned into numbers, FV schemes and FV solution. That's where the finite volume method comes alive. See you there.